Good morning and welcome to the Royal Swedish Academy of Sciences. The Academy met in session this morning to decide on this year's Nobel Prize in Physics, and we are now ready to announce it. And it took a little while for us to get in touch with the Nobel laureates, so therefore we are a few minutes late. I apologize for that. I'm Göran Hansen, I'm the Secretary General of the Academy. And with me today is, on my right, Professor David Haviland, who is the chairman of the Nobel Committee for Physics. And on my left, Professor Ulf Danielsson, who is, among many other things, also a member of the Nobel Committee. Before we announce the prize, I would like to thank all of you who are here in the session room today. And I regret that we have to operate under restrictions imposed by the corona pandemic, and I really appreciate that you are complying with these restrictions, so thank you. I must also apologize to all the journalists who cannot be here in the session room this year. Normally we are close to 90 people in this room. Now we must be fewer than 30 persons altogether. And therefore, many representatives of the media will have to follow the press conference over a video link. We're really sorry that we could not admit you, and we hope for your understanding, and we're offering interviews with Nobel Committee members and other experts immediately after the press conference. So, thank you for your understanding. Now, over to the Nobel Prize in Physics. This year's prize is about the darkest secrets of the universe. Årets Nobelpris handlar om universums mörkaste hemligheter. Kungliga Vetenskapsakademin har beslutat att utdela 2020 års Nobelpris i fysik med ena hälften till Roger Penrose för upptäckten att bildandet av svarta hål är en robust förutsägelse av den allmänna relativitetsteorin. Och med andra hälften gemensamt till Reinhard Genzel och Andrea Ghez för upptäckten av ett supermassivt kompakt objekt i Vintergatans centrum. The Royal Swedish Academy of Sciences has today decided to award the 2020 Nobel Prize in Physics with one half to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. And the other half jointly to Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy. Die Königliche Schwedische Akademie der Wissenschaften hat heute beschlossen, den Nobelpreis für Physik des Jahres 2020 mit Penrose für die Entdeckung, dass die Bildung von schwarzen Löchern eine robuste Vorhersage der allgemeinen Relativitätstheorie ist, und die andere Hälfte gemeinsam an Reinhard Genzel und Andrea Ghez für die Entdeckung eines supermassereichen, kompakten Objekts im Zentrum der Milchstraße zu verleihen. L'Académie royale des sciences de Suède a décidé ce jour d'attribuer le prix Nobel de physique 2020 avec une moitié à Roger Penrose pour la découverte que la formation de trous noirs est une prédiction robuste de la théorie de la relativité générale. Et l'autre moitié, conjointement à Reinhard Genzel et Andrea Ghez, pour la découverte d'un objet compact supermassif au centre de notre galaxie. Королевская академия наук Швеции решила сегодня присудить Нобелевскую премию по физике одну паладину Роджер Пенроуз за открытие того, что образование черных дыр является надежным предсказанием общей теории относительности. Вторую паладину равна Reinhard Genzel и Andrea Ghez за открытие супермассивного компактного объекта в центре нашей галактики. And you have the pictures of the new Nobel laureates on the screen behind me. Roger Penrose was born in Colwich in England and got his PhD at Cambridge University. He's now emeritus professor in mathematics at the University of Oxford. Reinhard Genzel was born in Bad Homburg vor der Höhe in Germany. He got his PhD at the Universität Bonn, and he's currently director at the Max Planck Institute for Extraterrestrial Physics in Garching in Bayern in Germany. And he's also a professor at the University of California at Berkeley in the United States. Andrea Ghez, finally, was born in New York City. She got her PhD at Caltech in Pasadena in California, and she's currently professor at the University of California, Los Angeles in the United States. Now, we are not requesting that the Nobel laureates come to Stockholm in December this year to pick up their prizes. Because of the pandemic, we plan for digital Nobel lectures and a digital prize ceremony with laureates participating over video links. We are still working on these events together with the Nobel Foundation and, of course, from now on with the laureates themselves. And we'll come back with more information as soon as it becomes available. But already at this stage, I can assure you that the Nobel laureates will receive their awards before the end of the year, and that they will be invited to Stockholm next time we can celebrate the Nobel Prize in the traditional way here in Stockholm in December. And with that, I'd like to ask David Haviland, chairman of the Nobel Committee for Physics, to make some remarks. David, please.
Thank you, Göran. On behalf of the Nobel Committee for Physics, I would like to congratulate the laureates in receiving the 2020 Nobel Prize. This year's prize celebrates the discovery of one of the most exotic objects in our universe, the black hole. For many years, physicists questioned the very idea of a black hole, treating it as a peculiarity in our theory of gravity. Roger Penrose showed that black holes might really exist, forming in a stable and robust process consistent with the theory of general relativity. Reinhard Genzel and Andrea Ghez led research teams to make precise observations over many years, which pointed to the existence of a supermassive black hole in the center of our very own galaxy. My colleague in the Nobel Committee for Physics, Professor Ulf Danielsson, will tell us more about the contributions of this year's laureates to the discovery of black holes.
Thank you, David. And now, Ulf, the floor is yours.
As early as the end of the 18th century, the English astronomer John Mitchell and the French scientist Pierre-Simon Laplace speculated that there might exist objects with a gravity so strong that not even light can escape. We now call such objects black holes. To create them, you would need to compress the sun into a region only a few kilometers across, or to squeeze the Earth down to the size of a pea. But it was only in 1915 when Einstein formulated his general theory of relativity that we had a mathematical framework powerful enough to describe such objects. Physicists, Einstein himself included, were confused for decades. The mathematics was too complicated. Could something like that actually occur in a real universe? And then, in 1965, inspired by the discovery of new violent phenomena in the universe in need of an explanation, Roger Penrose published a remarkable paper. He introduced new mathematical tools and proved with mathematical rigor that the formation of black holes is an inevitable consequence of general relativity. In a universe governed by general relativity, the formation of black holes is a natural and expected process. Let us study now a black hole a little bit more closely. In general relativity, there's an intimate relation between gravity and time. Down at my feet, time runs a trillionth of a second slower per hour than it does up in my head. And if you have a black hole, time even seems to stand still at the horizon of the black hole. Now, I can point towards the black hole and say, there it is. There is the center of the black hole. My finger is stretched along a direction of space. But if I then bring my finger a little bit closer and let the tip of my finger go through the horizon and enter into the interior of the black hole, I will make a startling and somewhat worrying discovery. The direction inwards is now time, and the tip of my finger will be in my far future. And it will be as difficult to pull my finger back out again as it would be to travel backwards in time. Furthermore, my finger will be torn apart, and the tip of my finger will be carried by time all the way into the center of the black hole, where time itself ends, and the known laws of physics cease to apply. But if such objects now actually exist in the real universe, then how could you find them? Well, actually, already in 1783, John Mitchell had an idea. What if there are other luminous objects, such as stars, moving around the black hole? Then one could infer the existence of the black hole by following the motions of the stars. But it would take more than 200 years before this dream would come true. And it was Reinhard Genzel, Andrea Ghez, and their teams who did it. They turned their telescopes towards the center of our galaxy, 26,000 light years away, where there were suspicions that something strange was going on. The heart of our galaxy, the heart of the Milky Way, is hidden inside of a dense cloud of dust. And you have to look in the infrared to reveal its secrets. What they found was incredible. They could see several stars moving around something that they couldn't see. And it was one star in particular that caught their attention. It took the star around 16 years to complete its orbit. At closest approach, it was no more than 17 light hours away from the invisible object. Calculations show that 4 million solar masses is hiding there. There is no other explanation than a supermassive black hole. This year's laureates have uncovered secrets in the darkest corner of our universe. But this is not just an old adventure coming to its triumphant conclusion. It's a new one beginning. As we probe ever closer to the horizons of the black holes, nature might have new surprises in store.
Thank you very much, Ulf, for that excellent introduction. And now it's time for questions. When you ask questions, if you could please push the button on the microphone stand so that it comes, your voice is picked up. Actually, we hope to have one of our new Nobel laureates with us on a phone line. Dr. Andrea Ghez, are you there?
Yes.
Hello, this is Göran Hansen again. I'm the guy who called you about an hour ago to give you the good news. And we are now in the middle of our press conference, and I wonder if you're ready to take some questions.
I'd be delighted.
Who would like to start? Thomas Honheide, fast as always.
Hello, Professor Ghez. Congratulations. I'm just curious. This is Swedish television public service. I'm just curious to hear what went through your mind when you saw that sign that there must be something lurking in the middle of the Milky Way.
I think the first thing is doubt. That you have to prove to yourself that you're really seeing what you think you're seeing. So both doubt and excitement. It's that feeling of being at the frontier of research, where you have to always question what you're seeing. So it's a combination of things.
More questions? Yes, I think it's David Keaton from Associated Press. You'll get a microphone there.
Yes, David Keaton from the Associated Press. Thank you, Professor. At this moment in time, the research that is being rewarded here today dates back for decades. And like you just mentioned there, this disbelief at the beginning, the importance of science and the belief in following the facts is quite crucial. At this moment in the United States, where science is somewhat in doubt, what message do you have maybe today?
Oh, that science is so important, and pursuing the reality of our physical world is just critical to us as human beings. I think today I feel more passionate about the teaching side of my job than I have ever, because it's so important to convince the younger generation that their ability to question and their ability to think is just crucial to the future of the world.
Thank you. Please, we have a question. So, Professor Ghez, did you hear the questions?
Unfortunately, I did not hear that question.
Okay, could you repeat then?
Okay, you're the fourth woman to receive this prize. What do you think about that? That was my first question. And the other question is, do you understand what's happening inside the black hole? I mean, time is stopping. What time is it stopping at? Is it stopping now or at the end of the time? Or, well, do you have any way of explaining that so that we can understand it?
I did hear that, those two questions. So let me take the first. I'm thrilled to receive the prize, and I take very seriously the responsibility associated with being, I guess, as you said, the fourth woman to win the Nobel Prize. I guess I hope I can inspire other young women into the field. It's a field that has so many pleasures, and if you're passionate about the science, there's so much that can be done. Let me take the easier question, which is almost, what is the black hole? We don't know. We have no idea what's inside the black hole, and that's what makes these things such exotic objects. They really represent the breakdown of our physical understanding of the laws of physics. So that's part of the intrigue, is that we still don't know. It really pushes forward on our understanding of the physical world.
Question over here.
Hello, this is Jörn Spolander from TT News Agency, Swedish News Agency. First, I want to congratulate, of course, to the prize. And then perhaps you just answered it, but how would you say that this discovery of a black hole far, far away has changed life here on Earth?
Well, it really represents the basic research. You don't always know how it's going to affect our lives here on Earth, but it is pushing the frontier of our knowledge forwards, both from the point of view of pure physics, understanding what a black hole is, and then also their astrophysical world in the formation and evolution of galaxies. And so today we really accept that these objects are critical to the building blocks of our universe.
Any more questions to Professor Ghez? If not, thank you very much again, Professor Ghez, and we'll be in touch about the arrangements for December. But thanks so much for being with us at the press conference.
Thank you.
Bye-bye for now. Now, any questions for the panel? All crystal clear? If there are no further questions, thanks so much. Now there will be individual interviews taking place here, out there, and nearly everywhere in the building. And our staff will help you find your way. Please be careful and keep the distance when you exit the room. And then, of course, you're all very welcome back tomorrow for the Nobel Prize in Chemistry. Thank you.
Ulf Danielsson, can you summarize this year's Nobel Prize in Physics, please?
Yeah, it consists of two parts. There is one part which goes to Roger Penrose for the theoretical understanding or even prediction of the existence of black holes. I mean, the history of black holes go back, way back in time to the end of the 18th century. And then, of course, through Einstein's general relativity, we had the tools to actually start to describe these objects for real. But since the mathematics is so complicated, it took several decades before one really was able to understand what's going on. Could such objects actually form in the real world? And that is what Roger Penrose did. He understood the mathematics, he introduced new tools, and then could actually prove that this is a process which you naturally can expect to happen, that a star or something else collapses and turns into a black hole. Before Penrose, that was far from clear. Many thought that such objects were only mathematical artifacts that couldn't form in the real world. So Roger Penrose, he laid a foundation, the theoretical foundation, so that we could say that yes, these objects exist, we can expect to find them if we go out and look for them. And this was sort of a journey that started in the mid-60s. And what Reinhard Genzel and Andrea Ghez have done is to prove really that such objects exist. And they found one, a supermassive black hole in the center of our Milky Way. And the way they did that was that they monitored stars which were orbiting around something that they couldn't really see. And that, of course, required very sophisticated equipment to be able to do this and make these observations. So it took several years. And then this work has continued, and one has been able to look further and further in and closer to the black hole to start to test general relativity.
So what is a black hole?
Well, so far, I mean, what the current understanding of a black hole is that it's sort of it's a region in space where gravity is so strong that not even light can leave it. I mean, if you think about the Earth, on the surface of the Earth, we have what's called an escape velocity, which is equal to 11 kilometers per second. That means that if something is directed upwards with that speed, then it will leave the gravitational field of the Earth and never come back again. Now, a black hole, that's sort of an object, you would say, where the escape velocity is like the speed of light. Now, in fact, what turns the structure of a black hole in general relativity turns out to be very much related to the structure of space and time. So it's like a region in space and time which is so warped and curved that it's impossible to find our way out again. In fact, what happens is that when you reach the boundary, the horizon of the black hole, time, I mean, we always carried on by time. You cannot compete with time. I mean, there's no way to stop time or go back in time. But the point is that when you go inside of the horizon, the direction of time is pointing inwards towards the center of the black hole, where it actually ends, because in the middle, that's sort of where the direction inwards ends. And that means that the way that you're caught by the black hole, it's as powerful as the flow of time itself. So it's as difficult to get out of a black hole as moving backwards in time. That's our current understanding of a black hole. That is what general relativity predicts. And everything that we have seen so far is compatible with that picture. Still, and that is of course why one continues to do all these observations and measurements, is that it could be that there is something else, something different that you will be able to discover when you move really close into the horizon. So we cannot say for sure what's going on, but we know that these objects exist, but we are not quite sure about their real properties. There could be new physics, there could be surprises.
There have been a lot of black holes in science fiction, actually, and there the end of time is also a beginning of something else inside the black hole. You cut the time and go or travel out in another time, past time, for example. Would that be possible, you think?
It's not very likely, actually. I mean, the most likely possibility is, in fact, that it's a one-way road, and there is no escape. There's no way to come out somewhere else. Of course, I mean, who knows? But according to the current theories, our current understanding, if once you're into a black hole, I mean, that's the end of it, basically. Well, who knows? I mean, it certainly marks the bounded limits of our knowledge, and you can start to speculate in various ways. But a good guess is that once inside the black hole, there is no way out. Just the end.
But you mentioned that there are black holes actually out in the space. So where are they?
Well, there are probably lots of black holes. The one which is awarded this year's prize, the discovery of the black hole at the center of Milky Way. But probably there are many similar examples all through the universe. Or every galaxy is probably hosting a big black hole in its center, many which are much larger than the one in our Milky Way. And then furthermore, we expect there to be lots of smaller black holes sprinkled across the Milky Way, which are the products of a supernova. I mean, stars which have run out of fuel and exploded, and then giving rise to these black holes. So black holes are all over the place.
So how dangerous are they if we come close?
Well, not especially dangerous at all, really, because the likelihood for us to encounter a black hole is really very small. It might very well be that there are black holes among the stars, black holes that we cannot see. But I mean, remember, I mean, it's very rare that you would collide with another star, right? Another star would collide with our solar system. That doesn't really happen, and there is no difference with stellar mass black holes which are moving around in the Milky Way. They will not just come and hit us. The probability for that to happen is very, very small.
But what would happen if you come close to a supermassive black hole?
Okay, now let's say that you were able to travel on purpose and wanted to examine such a black hole. Then it's actually the bigger it is. Because if it's a really big black hole, like the one in the center of the Milky Way, then you can, without really getting hurt in any way, you can travel all the way towards the horizon and even cross the horizon and enter into the black hole without being stretched by gravity. If the black hole is small, like the ones with just a few solar masses, then you cannot even get close before gravity will pull you apart. If you jump in with the feet first, then gravity will be stronger in your feet than in your head, and you will be just torn apart. But for a big black hole, you could actually imagine such a journey into it. Then, of course, it's a dangerous place still, because there might be lots of other stuff happening. I mean, there might be hot gases and plasma, which is swirling around the black hole, and dangerous radiation. But as far as gravity is concerned, a big black hole is not really that dangerous. Of course, I mean, once in, you cannot get out again, but otherwise it's okay.
Yeah, it's just the end.
It's just the end, otherwise it's fine.
Reinhard Genzel and Andrea Ghez came actually quite close by observations.
They did, yes.
Did they expect this prize?
Sorry,
Did they expect the Nobel Prize?
I have no idea.
What did they say when
they were
came?
very, very happy, obviously, clearly, and that was a very pleasant experience. I mean, to share that moment with them.
Thank you very much, Danielsson.